I think the recording is already on, so we might as well get started, and then yeah, we can see how it goes. I don't want to miss the demo. So thanks everybody for joining. This talk is about accelerating distributed joins in Apache Hive using runtime filtering enhancements. Yeah, thanks Martin for letting us know. A few words about us. I'm Panos or Panagiotis. I'm a software engineer at Cloudera, part of the runtime team, and I'm currently working on Apache Hive, Orc, and Tez open source projects. Before that, I was a PhD student at Imperial College London, where I was working on distributed systems. My colleague here is Stamatis. He's also a software engineer at Cloudera. He's part of the query optimizer team, and he's working mostly on Apache Hive and Calcite project. He holds a PhD in data management from INRIA and Paris SAD University. So let me start by providing some background about Apache Hive here. Apache Hive was one of the first SQL processing systems working really well with Hadoop. It's been around for more than a decade, started back at Facebook, back at 2008, and it has gone through major changes over the years to broaden the project scope and the use cases that it would cover. So we're currently in a position that we can run low latency multi-tenant queries on petabytes of data. But of course, this was not always the case. In the early days, Hive started as a scalable SQL processing system, mostly targeting batch processing on read-only data. It worked only with MapReduce, and it supported only a subset of the SQL language called HiveQL. In its second and third version release, Hive went through some major changes to improve its latency, its scalability, and its SQL support. This was also known as the Stinger Initiative, Initiative, which was a community initiative to change the execution engine in Hive, including Tez and Spark runtimes, adding vectorization. So we now have batch processing on column vectors instead of just rows, and also replaced the traditional container execution model with persistent daemons called long live and process, also known as LLAP daemons. These LLAP daemons enabled low latency query execution and data caching across users and queries. So we're currently on the fourth version of Hive, Hive 4, and the community introduced a number of extra compiler runtime optimizations to even further improve its efficiency, such as materialized view rewriting, anti-join support, semi-join reduction, and lazy materialization. And those last two optimizations is the focus of today's presentation. So all these optimizations I mentioned, there are many, many more that I don't have time to mention, enabled the users and Cloudera customers to do crazy things with Hive that were not doable in the early versions. So we have customers in Cloudera in a variety of sectors like banking, telecommunication, automotive, life sciences, and technology that run 250,000 BI queries on a single cluster. Or we have thousands of analysts running sub-second average latency queries on a petabyte of data. And those things were pretty unthinkable in the early days of Hive, and even until very recently, they were not even doable. So the community did a great job over the years to improve this project and move a step forward and support all those use cases. For those of you who are not aware of the Hive design or Hive architecture, let me go really, really fast through it. So we have on the upper left side, users that connect to Hive Server 2 to submit their queries. To submit their queries, they're using the favorite client like ODBC, JDBC, or Beeline. Beeline is a thin client included with Hive distribution. Hive Server 2 will parse those queries and compile them, and might also contact the metastore. The metastore is the data catalog of the cluster containing metadata information about the tables and column statistics that help the optimization of the query plan. After compiling the queries, it will create a DAG of executable tasks that will be submitted to the EM. The EM is part of the query coordinators, and as you can see here, we have a few coordinators in this cluster, in this Hadoop cluster. Coordinator will be responsible for the execution of the query and also returning the results back to the user. For the execution part, it will submit the tasks, the work, to each LLAP daemon. And within the LLAP daemon, we have a bunch of executors running those tasks in parallel. Those tasks might also retrieve some data, depending on the execution, from the storage layer. The storage layer can be anything from HDFS, an object store like S3, or any external engine like Apache Druid. So if we zoom in a bit on the LLAP daemon anatomy to see how the actual execution happens, we have the query coordinators again on the left, which are outside of the LLAP daemons, of course. They submit the tasks to a work queue, and those tasks are known in Hive as query fragments. Those query fragments are pretty much a fancy word of saying one or more operators that are part of a single query, and they run together. Those fragments enter the work queue, and we have a priority queue within that work queue with some smartness built in it. The smartness prioritizes these fragments based on the expected runtime. So shorter runtime fragments will always be higher priority because we assume that those fragments are more sensitive to latency. Then on execution component, we have a bunch of executors that are in parallel pulling fragments from that queue. And whenever they're done, they will pull another fragment and another fragment until there is no more work to be done. Then on the right side, we have the IO layer consisting of the IO queue and the IO elevator layer or component. Each IO request is given asynchronously to the IO queue, and then the IO elevator component will initialize the appropriate reader for its request for the particular data format we're reading data from. And then it might also contact the data storage layer to retrieve the data from S3 or from HDFS. And because this can be an expensive step, retrieving data from an external layer, we also have an optional data caching layer. This data caching layer is pretty much a read-through cache. And whenever we retrieve some data, the IO elevator can check if the data is already there within the cache. We will decompress it and give it back to the execution engine without going to the external layer, which is the expensive step I mentioned. Of course, this data cache is fine-grained and compact. It's fine-grained because we keep columns and row groups that were recently accessed. So we don't keep whole files. We keep row groups, which works really, really well with columnar data formats, as we'll see later on. And it's compact because we store data encoded to minimize the memory footprint. So we don't store just raw data. We store them encoded there. Now, for the remaining of the presentation, we're going to split it in two parts. Since we have two optimizations we're going to talk on, it's the Semiign reduction and lazy materialization, after talking a bit about the data pruning and filtering optimization. So now, handing over to my colleague Stamatis, that is going to take over from here.
So, hello, guys. Thanks for my side as well for joining. So, as Panos said, let me get straight to the point of today's talk, which is pruning data as early as possible. So we are going to see together how is this done and why we are doing it. So there are many optimizations and techniques to prune data early, and among those, it is Semiign reduction and late materialization that we are going to see today. And why we are doing this? Because the sooner that we prune the data, the cheaper will be the operations afterwards. So we can reduce memory footprint, disk and network I/O, and we can also save CPU cycles. But let's make all this a bit more concrete. So let's take a specific example. So this SQL query asks for the products that were returned due to the fact that the customer found a better price in another store. And for all this, we are going to return the net loss for each product. So the query plan is quite straightforward. We have a scan of two relations, the store returns, which is the fact table, and the reason relation, which is the dimension table. We perform a join on the reason surrogate key on both sides. We compute the result, and then we apply a filter on the reason description based on the specific condition. And finally, we are going to project only the things relevant to our result, which is the net loss column. Now, just a bit of notation with all these boxes that appear here. For every horizontal set of boxes, we have a tuple, so a row, and the vertical boxes denote columns. So let's start applying optimizations for pruning data. One very, very well-known and widely used optimization is a filter pushdown. So in this case, we are trying to push the filters as close to the bottom as possible. In this case, the filter depicted here can go below the join. And what this has as an effect is that, as you can observe here, if we perform the filter and then we join this side with this, then the result of the join is much smaller than this huge block of tuples that appears here. Just a small thing that I forgot to mention is that the number of rows that appears here, it's just proportional to the amount of data that in the result of the join or in the size of the relation. So it's not entirely accurate with the actual number of rows. So we don't have only 9, for instance, here. Now let's see another very, very common optimization that is also widely used is what is called project push down. So if you notice here, the result of the query needs only the net loss column. So it is not important to bring back everything, every column after the join, but we can remove those that are not needed. Concretely, here we are going to keep only the reason surrogate key and the net loss coming from the store returns relation, because we need reason for the performing the join and net loss for the result. Same goes for the other side. And in the end, here we have the same number of tuples, but if you see, we have only 2 columns. So the tuples are much, much thinner. And again, this leads to less data, less CPU, less memory, etc., etc., etc. Now, let's talk about another optimization, which is a bit less known, but also very important. And it's called semi-join reduction. So many people may have observed already that what happens here is that we are using the right side of a join just to reduce or prune the results of the left side of the join. Because in the end, the columns that appear on the right side are not used in the result. So what happens is what this operator does, the semi-join, is exactly this. So basically, we are only using the results from the left side of the join, and the right side is used only from pruning the data. And essentially, this result of the join is again thinner. So we are sending less data to the operators that follow. Another very powerful optimization is late materialization. So till now, we assume that when we get the result from the scans, so here, for example, for the store returns, we have tuples that are materialized, decoded, and uncompressed, and they are in memory. But this is not necessarily necessary, because as you have seen here, we need only 2 columns to propagate further. So instead of decoding and decompressing everything, we just load from the disk the whole block of bytes, compressed and encoded, and then we decompress and decode only the things that we need. So in this case, it will be only this column here and the net loss column here. And same goes for the other side. So this is another optimization that we are going to see later on today, which is called late materialization, because we materialize data when it's really necessary. Now, if we put all this together, and something that should be all straightforward till now, is that from the baseline that we didn't perform any data pruning till the end that we performed all the optimizations on the right side of the slide, the gain is significant. The performance gains is significant. If we squeeze all these boxes together, then the gain becomes much more evident, where here we have significantly less data. So point to keep is that pruning data, point that I want you to keep is that pruning data early is very important. So let's talk about a bit more about semi-join reduction, and in particular, how is this done in Hive? You might have seen this optimization with some other names, namely invisible join, selective join push down, or otherwise sideways information passing. No matter how you call it, the behavior is the same. Between the semi-join and the reduced join, all the operators will treat less data. And as a result, we will have less network and disk I/O, we will gain CPU cycles, and will decrease the memory footprint. Now, let's take a slightly more complicated query just to have a concrete example and have some concrete numbers. I don't want you to stay a lot on the query because it is there. You can find it afterwards in the slides. But notice that we have quite many operations. We have aggregates, we have sorting, and we have two joins and filtering. So for the semi-join reduction, I will simplify a bit the example so that we don't get lost. So let's just call all this part subplan A, and all the part after the join subplan B, so that we focus only on the part that's really, really relevant for the semi-join reduction. So instead of boxes, now we will talk with numbers, and these numbers are accurate, correct numbers from TPC-DS dataset, but a very, very small scale factor. So from the fact table, we have around 2 million rows, and from the dimension tables, or on the subplan A, we have 8,000 tuples, and the result is also 8,000 tuples. So what happens, as we said, we are in Hive and in a distributed setting. So let's make the example more appropriate for it. Let's assume that all the data for the stored sales fact table are located in node 1, and the data for subplan A are in node 2. And let's assume that the join is performed in node 3. Again, this is a very, very simplistic example, since what happens in practice is that normally the data are distributed in various nodes. But just to show concretely the benefit of the semi-join reduction, we are going to use a very, very simple case. Now, if we go from the number of tuples to the size of the relation, we are going to notice that we are sending from node 1 to node 3 to perform the join around 46 megabytes, and from the other side, a few kilobytes, and then the rest to the rest of the operators. But comparing this number with this, we would like to, if possible, to reduce this number, this 46 megabytes. And as you guessed, since we are talking about semi-join reduction, we are going to perform this using a semi-join. So the condition of the semi-join is exactly the same with the inner join, but as we said, the semi-join will keep only the tuples from this relation, from the left relation. And we are going to use the right relation only for pruning data. So we are going to send relation A or subplan A to the other side, just to reduce the number of tuples coming from the stored sale table. And so far, this is what happens. So from the 2 million tuples, we drop down to the 8,000. And assuming that the semi-join is performed on the same node with the scan, what happens in terms of traffic is that we manage to drop the 46 megabytes, to only a few hundred kilobytes. And putting things side to side, in terms of total network traffic, with the semi-join, we have around 400 kilobytes, and without the semi-join, we are in 46 megabytes. So the difference in I/O is 2 orders of magnitude. And same goes, although we talked about I/O, the same goes for CPU and memory. Now, let's go a bit more concretely how it is done in Hive. It is done in 2 steps. So we don't have a semi-join here, but we have an aggregation and a filter. So for the aggregation, we compute the minimum and maximum for each column participating in the join. And then we create a Bloom filter with all the values with the hash of the columns participating in the join. So here the Bloom filter is actually our summary that is going to be used to perform the semi-join. And on the side of the fact table, the filter looks like this. So we have for each column a conjunction that a between predicate that verifies that the column value is between the min and max coming from the aggregate. And then after we verify the between condition for both columns, we perform a lookup in the Bloom filter. So this is why It's called also sideways information passing because we are passing things from the right side sideways to the left side. And what we gain by performing the Bloom filter semi-join is that we manage to decrease even more the size of the data that are propagated from node 2 to node 1. So instead of sending the whole relation and sending, in this case, 64 kilobytes, we are sending, in the end, only 9 kilobytes, which is actually mostly the size of the semi-join of the Bloom filter, sorry, which is the size of the Bloom filter. And just a small note, we are talking about Bloom filter. So we are talking about a probabilistic data structure. So in the end, we may have false positives that are propagated from node 1 to node 3. But by choosing an appropriate size from a Bloom filter, the probability can be really, the probability of having false positive can be really small and rather insignificant. So by performing a Bloom filter semi-join, we reduced even more the cost, the total I/O cost, and essentially, because we prune data early, we reduce the CPU and memory of the following operators. Now, just a quick overview of how it is done in Hive. Basically, it is divided into 4 phases. The first phase creates some synthetic predicates on the side of the fact table. Then this synthetic predicate is expanded to create the semi-join branches. And afterwards, because we have only single column semi-join branches, we have a phase that merges these single column semi-join reducers to multi-column ones, improving the accuracy of the Bloom filter. And this third phase is actually quite recent, so it has been introduced in these Zira issues mentioned here, and it's been only 2 months that it's on Hive Master. And last, because we are introducing optimizations, semi-join reducers aggressively, there is a last phase that tries to remove based on cost and other factors. So apart from that, I have some slides at the end of the presentation. Really, an example shows how this works. But since we are not have much time, I will now pass to my colleague Panos to talk to you about lazy materialization.
Thanks, Stamatis. So let's move to the second feature that we're going to talk about today, which is lazy materialization. It has also some other names that you might be aware. It's also known as row-level filtering or lazy decoding, or even probe decode, as we call it on Apache Hive. The goal of this feature is to save CPU cycles and reduce memory allocations by actually avoiding materializing or decoding rows that are not going to be needed down the line for the validation of the remaining of the query or for the remaining of the expressions. And lazy materialization is an important feature because even when we have optimizations such as semi-join reduction, and we filter as much data as possible, we can still end up decoding more data than we actually need. And the reason for that is partly because of the way columnar formats such as org or Parquet store information and indexes. For instance, in org, data is organized in tribes, and within each tribe, we have a number of row groups storing metadata and indexes per thousands of rows. So that by default, it's 10,000 rows. The problem here is that as a row group is the finest level of indexing we have in org. Even when we have just a few keys that match within a single row group, we have to read, decode, and push down the pipeline all thousands of rows across columns for that particular row group. And this is just a waste of resources. To give you an example, we run Query 55 from TPCTS on 10 terabytes of data, which is a low selectivity query. And as you can see on the figure, on the x-axis, we have the selected row groups for a particular table. On the y-axis, we have the density number, which is pretty much the number of matching keys per row group. And as you can observe in this figure, even though we have a low number of matching keys in general or in total, all row groups were selected because these keys, these matching keys, were distributed across row groups. And this can happen a lot in reality. In fact, we found out that for this particular query, this low selectivity query, we spent almost 27% of CPU time on decode batch method. This decode batch method is taking row groups, decoding them, and pushes them as column vectors down the execution pipeline. The worst part about this is that even after doing all this work, most of the rows in these vector batches will be dropped eventually because we have only a few matching keys in those vector batches. And to understand why this is the case and why this happens, we have to understand how data is organized within files with the org format, or in a similar manner to other columnar formats. So each org file contains a group of groups of raw data called stripes, and at the end of each file, we have the file footer. The file footer contains the metadata of the file, pretty much file level statistics like the file schema, etc. We have stripe information such as rows, column type, column aggregation statistics, and more importantly, the location of those stripes. And at the end, at the very bottom, we have the postscript, which contains the compression details, buffer size, and information how to read the remaining of the file. So an org reader that wants to read a particular file will have to read first the postscript, then the file footer, and then it can directly point to the location of the stripes within that file. Those stripes contain the actual data with some metadata on top, organized in columns, as it's a columnar format, of course. And as you can see here in the figure, we have a few stripes, and from top to bottom within each stripe, we have the index data with green, we have the row data with blue, and we have the stripe footer with red. The stripe footer contains a list of column streams and their locations. Column streams point to row data, which is in blue, that are the actual data used in table scans and query answering. And we also have some information about each column encoding. So by default, every column is encoded in org. At the top, we have the index data. The index data contain offsets that enable seeking to the right row group within a column. And we have statistics like the minimum, the maximum, and the sum values of each column per row group. This row group size is, of course, configurable. By default, it's 10,000 rows, but we can configure it to be less, to be more fine-grained, or more to be less fine-grained. But of course, as you understand, there is a trade-off here between the row group size and the metadata size. So we don't want to go too low. And all these indexes I mentioned, like the file level indexes, stripe level indexes, and row group indexes, actually enable us to get only the row groups that are of interest for answering the query that we're interested at. So execution engines such as Hive and, of course, Spark and other execution engines leverage those indexes and can leverage them by using these simplified expressions called sargs in Hive. These sargs are supported by org, the org reader itself, and they actually restrict the number of rows that are returned to the execution engine. And because they're simplified filters, in reality, they have their own limitations. First of all, they cannot support UDFs or columns with relationships, like the example we have below. And as you understand, we can only eliminate at the file level, at the stripe level, or at the row group level, which is the finest level of indexing we have on org. This means, however, that even for a simple expression like below, where we project 3 columns and we apply a more detailed filter, one of them on X in this particular case, we will have to decode all the row groups across all these columns like X, Y, and Z, and then the process engine itself will have to do the filtering afterwards, which can be pretty expensive in reality. And this is one of the many practical cases that require a more fine-grained filtering mechanism for storage formats like org. And this is exactly what we did with org 577. So this is how we enabled fine-grained low-level filtering for org by reading a subset of the columns and applying a more detailed filter afterwards and using this information, as we'll see in the steps below. So this filtering mechanism works in 3 steps. In the first step, we expand early the columns that we apply the filter on. In this case, we're going to lead totally column X and all the rows from that column. On the second step, we're going to apply the filter by picking up the rows that are passing that filter. And we can do that by setting a selected array within each column vector, keeping track of the rows that actually match. And on the third step and final step, we're going to use the selected array to read and decode only the rows that satisfy the filter from the remaining of the columns, being Y and Z. And instead of reading thousands of unneeded rows, which is the default case, we're going to end up reading only the few rows that match in our example. And to give you an idea of the benefit we get with this row-level filtering mechanism, we extended the benchmark given with org, which is using real data sets such as taxi, sales, and GitHub data sets, and projects a number of columns. So as you can see on the x-axis, we're playing with the selectivity. We increase it from 1% to 100%. And on the y-axis, we have the runtime it takes to project those. So for this particular graph here, we use a sales data set. We projected 20 columns. We applied a more restrictive filter to one of them. And as you can see, for 1% selectivity, we have 56% in runtime, while selecting 10% has 44% decrease in runtime. So pretty impressive. In general, as a key takeaway here is what we found out is that it's always beneficial to filter all those data as early as possible to end up with less data down the pipeline in your execution engine. So this is what you can get out of this figure. To implement this feature, we had to introduce the filter context, which is pretty much the selected array that I told you as part of this Hive Jira. And we also had to extend the orc reader logic with this new option. This new option takes the column names that are going to be early expanded and a filter. The filter is a callback pretty much that can implement any kind of logic. And currently, we implement this logic on Hive itself. The new orc reader works in 3 steps, as I mentioned: early expand, evaluate the callback, and then decode only the rows that are out of interest. And then, more importantly for us, Hive can directly benefit from this row-level filtering mechanism that is implemented on orc when scanning and filtering data. And without going into too many details about this query here, we have a catalog sales fact table, and we have a dimension table on the right side where we apply a more detailed filter on 2 columns. And what you can take from this is that instead of decoding all 1 million rows on the right side across all 3 columns, and then apply the filter on the 3rd step, what you can do is you can early decode the filter column, which are 2 out of these 3 columns, and then decode the remaining of the columns only for the ones that satisfy the filter. So in this case, instead of decoding 1 million data STA rows, we're going to decode 8,000 of those rows. And this is what we call static row level filtering in Hive. We also have a more advanced dynamic row level filtering mechanism that actually works within map join tasks. And again, without going into much detail, those tasks use the broadcasted table on the streaming side to decode only the matching rows from the secondary columns on the fact table. So in this case, it's item STA column. And feel free to check out the latest Hive source code, enable the optimization, the probe decode optimization, and you can find a few query plans, and you can see how this optimization kicks in. And since we have some time, I'm going to show you a little demo that I just prepared. So let me share my other tab to see. Yeah. So what we have here, I hope you can see my screen. Well, what we have here is the Data Analytics Studio platform, and I just ran 2 very same queries. So this is query 43 from PPCDS benchmark. And both those queries run on 10 terabytes on Azure using 4 executors, if I'm not mistaken. And query A is with optimization, the probe decode optimization enabled, and query B is the optimization disabled. So if you don't believe me, yeah, this is a difference here. So the one, the flag is false and the other is true. The plan itself is exactly the same as you can see here, but there is one slight difference on the store cells, which is the fact table scan. You can see we have the probe decode details here. It's actually using the hash table that is propagated to filter out as less rows as possible, while on the second query with the optimization disabled, we don't have that there. And even for this simple query, you can see that we have a huge difference in runtime. So the optimized version with probe decode enabled runs in 55 seconds, with optimization disabled runs in 1 minute and 50 seconds. And of course, you can check the plans here, and you can check the data flow and everything. But if you dive a bit deeper, you will see that the main difference is on the number of decoded rows. So in the optimized version, we have 2 billion rows decoded in total. And on the second, with the optimization disabled, we have 5.5 billion rows. We still have some time, so I'm gonna just switch to my final slide, which is gonna be this slide. That I just want to mention that this is not a single person's effort, it's just a community effort, and the community has done a lot of work moving Hive from what it was, like a batch processing engine, to interactive. And the system as it is today can thrive in many other environments. That's why we are now working on Hive on the cloud on Kubernetes as Cloudera. And we have long-running Kubernetes cluster with your data plane shared services like data catalog. And then we can have a ephemeral clusters with high server to LLAP daemons to submit queries. And of course, we have a lot of nice features like elastic compute resources, spot instances, multiple versions of Hive, etc., etc. And feel free to check out the CDP platform where we can provide those services both for private cloud and for public cloud. And with that, I would like to conclude and happy to take any questions.
I see, Panos, that there is a question about lazy materialization.
Yeah. Got it. So is lazy materialization possible for if your table is stored in Parquet? Good question. So by default, this lazy materialization mechanism is implemented on org. Similar ideas can be ported to Parquet, and this is something that we have been discussing to do in Parquet, but we currently haven't done that. However, in Hive itself, all the AC tables are going to be stored in org. So if for any reason you do a conversion, for example, from reading Parquet data and storing them as managed tables, by default it's going to be in org. So by default you're going to get these optimizations out of the box. If you want to store, if you're going to query external tables on Parquet, the answer is no. But if you port and you move your data internally, you're going to have this out of the box. But the ideas apply there as well from a research point of view, let's say.
Any other questions, guys? Somebody? Okay, here is another one. Will this be LLAP only or also CDH5?
Do you want us to talk about your Semiign reduction? I can answer about the lazy materialization feature. So for lazy materialization, the static part. So for lazy materialization, the static row level filtering can be supported on non-LLAP and LLAP environments. But the dynamic part that I mentioned with the hash table push down is actually only on LLAP. Yeah, but it's you can try it out on CDP public if you want. I'm not sure about CDP5. I have to check this if you're going to port that there. Currently, it's not there.
Semiign reduction, it's a good question if it makes sense in non-network speeds. Normally, I mean, as I said, I showed examples that that you gain a network I/O, but in practice, it's not only network I/O. The fact is that if between the scan and the join that you are reducing, there can be many operators, then instead of only saving the network I/O, you save also the additional processing, CPU memory, and whatever else comes with it for all of the operators in the middle. So if you check also articles about I think you will find it mostly with the name selective joint push down, you will see concrete examples. And actually this is why in some cases it can apply also to centralized systems, because the big difference, you can see it with a slow network. So with a slow network, you can easily see the difference, but it can also matter even if it is a centralized setting and there is no even not network I/O.
I believe we're running out of time. Just letting you know, guys, that feel free to reach out afterwards. We'll be around and we're gonna upload the slides. Yeah, but feel free to reach out. We're available, and thanks for staying with us.
Thanks a lot, guys, for being here. See you again soon.